Workshop. My name is Mark Vitale, and I'd like to talk to you about a performance improvement that we did for the VLserver. Some of you may be surprised that the VLserver would be worked on for performance. For a typical cell, usually it's the file servers and the clients that are the focus of any performance issues. VLservers are generally very low maintenance. They don't have very high hardware requirements, and they're usually not very busy at all. And the same for the PT servers as well. The database servers are generally very low volume for a typical cell, but what I'm going to describe to you is not a typical site. This site is one of the world's largest OpenAFS sites, if not the largest. I'm not aware of one that's larger, so yes, that's the most authoritative statement that I can make on that. But I'm not aware of a larger cell, or larger site. There's actually multiple cells at this site. Current count is over 120, and most of those cells are read-only cells, so the content is accessed by applications accessing volumes that are read-only volumes. And those volumes are propagated from read-write cells, so production or development cells, and then the information from those volumes is propagated out into multiple cells. So many of these cells are similar in content to each other. We also got 1,300 servers, way over 100,000 clients, and 40,000 containers, and millions of volumes. For the purpose of my presentation, this work was actually started maybe 2 years ago, and at that time, the size of the VLDB that I was working with as my model was about 1.7 million volumes. But the current largest cell at this site has 3.5 million volumes in its VLDB. So the growth of that was starting to have severe impact on performance of the entire cell at certain peak times. And it was determined through things that we're going to look at here in a second that was VLserver was the bottleneck. So the primary use for this installation, for AFS of this installation, is to distribute software. And so it can be very important for any of the applications at this site. If they're getting their software that they need to run for their business from AFS, but AFS is performing poorly, it has an instant impact on all the business lines that are trying to access that particular cell that's blocked on VLserver performance. The reason there are so many cells is there's a number of reasons for that. Certainly we want to have redundancy. There are also business reasons. Some of the cells are segregated by geographic areas or by business lines. And for technical reasons that I'm not aware of, that some of the people here could explain to you more clearly, some of the Windows clients at this site are also segregated into their own cell. And I think you said that it was just because the load model is different between the Unix clients and the Windows clients, so they perform a little bit better if they're in their own cell. Another reason to have, of course, multiple OpenAFS cells that are in different geographic areas rather than having one large cell that is geographically distributed is because of the latency of communicating between the different servers over a wide area over a long time. Latency really is the Achilles heel of the RX protocol. And so many people who want to distribute AFS content globally are forced to do this type of splitting the cells into geographical locations and then distributing content other ways than AFS between the cells. We know of a number of large sites that do that. Okay, so why is the VLserver RPC rate so high? And that's what we're really talking about. Load here is the number of RPCs that this VLserver, a given VLserver, can maintain. First of all, we have a VLDB that has several million volumes in it, as I've already mentioned, and that produces its own type of challenges for administration of the cell. When you have that many volumes, any type of administration at all is going to produce a large amount of load on the VL server. Moving volumes, cleaning up old volumes, doing releases. If you only have 100 volumes and you do a release every day, it's not a big deal. But if you have 1,000,000 volumes and you do a release of each of them every day, now we're talking about some serious load. And it's not just releases from within the cell, but we also have this subsystem that is in-house that propagates volumes from the read-write cells where the content is developed and tested to the places where it's actually used by users, to the read-only cells. That incurs some overhead as well on the VL server as we move volumes around and propagate them to the other cells. And then, of course, the housekeeping that I already mentioned, constant releases and moves and deletes of old volumes that aren't being used anymore. All of that adds to the load. And then you already saw that this site has many thousands of clients. And of course, clients are the ones that we usually think of that are generating a large amount of VL server load. Every time someone wants to access a new mount point or access a different volume, as they're navigating down the path to the data that they're interested in, that's going to be generating VL server lookups. And for small cells, that's not a big deal. But when you have many thousands of clients that are looking up these volumes over and over again, especially if the client's volume cache is relatively small in relation to the number of volumes that that client actually wants to use, then there's going to be repeated lookups. And not just normal lookups either, but you could also have the type of lookups where if a volume is created or there's some type of volume operation on that cell, even if it's a read-only cell, doing volume operations in that cell can generate read-write activity against the VLDB. So for instance, if you're going to be creating a new read-only volume for someone to use in their new application, that even though it's a read-only volume, of course it's going to generate read-write activity against the VLDB. And when that happens, when you create a new volume, the very first thing you have to do, or the very first thing the VL server has to do, is to check to see where that volume already exists. And that turns out to be a pathological case in the problems, the performance problems that we're talking about right now. So when I get to that point, I'll explain that a little bit more thoroughly. But that's why I'm calling out the lookups in their different categories, is that you can have normal lookups that a client would make to access a volume that exists. You have administrative work that would be accessing a volume that you really hope doesn't exist, and that's a negative lookup, but it's a normal negative lookup. And then there are also, whenever you have a very large installation, you can also have abnormal negative lookups. Someone has configured your application incorrectly. They're using a mount point that's obsolete, or the volume name is spelled wrong in the mount point. That can happen. Or the mount point was created pointing to a different cell that is offline right now. All kinds of things where the lookup that's generated to the VL server, that volume does not exist, but it's going to look it up anyway. And that generates quite a bit of load that's out of proportion to what's actually being done. Okay, I forgot to mention when I started that if there are any questions at all while I'm going through this, please feel free to interrupt at any time. Just raise your hand or speak out. I'm comfortable with taking questions and interruptions during the presentation. If you want to wait till the end, that's fine too. There will be a time at the end. But if you think of it now that it's okay to interrupt, and if it's something I'm going to be touching on in a few minutes, I'll just tell you that and say that, you know, I'll be getting to that in a few minutes. So don't feel any compulsion to wait and see what's going to happen. I mentioned briefly that this site is doing something that other sites do as well, where in multiple cells and content is moved from a development cell or from a read-write cell into a read-only cell, or maybe multiple read-only cells. There are a number of ways to do that we are aware of. Generally, they're grown in-house. This site uses an in-house system to do that. That's based on VOS tooling, of course. We're aware of another site that does that as well, that Matt works at, and they have their own in-house system. But I believe it's tomorrow, Marcio will be talking about, Andrew will be talking about one called CellCC. So I don't want to steal his thunder, but this is a common thing that occurs in OpenAFS, this need to be able to administer and move content between multiple cells. And Andrew and Marcio work on one for another client that is available for open source. It's not in the OpenAFS tree, but it's available on GitHub for anybody to use. And it does pretty much the same thing. It satisfies the same business need for large sites that have multiple cells and need to move identical content between all of them. Okay. Anything else I wanted to say here before I move on? I just want to clarify one thing. I said that this particular site has 3.5 million, or 3.5 million volumes, but the presentation here is going to be focusing on the number 1.7 million because that's the number we were using to model for our testing. Just let me clarify that what I mean by that. When I say volume, I'm actually talking about a volume group. So a volume group is one entry in the VLDB that's comprised of the read-write volume ID, the read-only if there's a read-only that exists, and the backup if that exists. So all three of those volumes, we're not counting those as individual volumes. We're really talking about volume groups here. Okay, and I'm not sure if it's mentioned in any of the presentations during this conference, but there is an implementation limit in the current VLDB of 14.5 million volumes. That's the most that you can get into a VLDB because UBIC has an architectural or an implementation limit of 2 gigabytes for the database. So that's the most you can get into an UBIC database. I'll be talking about UBIC some more tomorrow. I think that's why I'm honing in on this. But the idea that how many volume entries can you get into 2 gigabytes? And the answer is about 14.5 million. So this really is a very large database, and it is, it's not far from the implementation limit. So that is something that we probably be talking about a little bit more tomorrow. All right, let's move on. So because of the way that these cells are configured, because of the large number of clients, a large number of volumes, a large number of applications that are running in this site, it generates a large amount of VLserver throughput. And so something that would not be a problem at a smaller site exposes a bottleneck at this site in the VLserver. And the bottleneck particularly is in the number of RPCs that we can run in a second, the RPC throughput. So I've given an example here. Here you'll see that the most common RPC at this site is the RPC that clients issue to look up volumes. So it's VL get entry by name U. So when a client hits a mount point, it sees the volume name in the mount point, and then it calls the VLserver to find out what the volume ID is there. Once it has the volume ID, then it can ask the file server for that particular volume, because it knows which file servers hold that volume, and it knows what the volume ID is, so it can build a FID from that. The average execution time was determined to be about 3.1 milliseconds for this, so that translates into about 320 calls per second max. So if we have clients that are generating a load of more than 320 lookups per second, then the VLserver becomes the bottleneck for the application. And clients slow down, everything slows down, and there's really nothing that you can do about it. So how do we know this number? This is just a side note, but it may be helpful for some of you that you might not be aware of this facility that's in OpenAFS. It has a number of names. Sometimes you'll hear it called RPC stats. Sometimes you'll hear it called RX stats. But every OpenAFS component has this available within it. So whether it's the cache manager or any of the servers, you can specify this option. So I've said it's VLserver option here, but really that option works on any component. You just say enable process stats, and that turns on an automatic gathering within the RX stack itself of the number of times a particular RPC is called, the maximum time that it took to execute that RPC, the minimum time, average time, and there's even some statistical information in there, some square root stuff. So you can retrieve that using that RPC, but most people would just use the sample utility instead, and it's not built by default. You have to go build it yourself. But if you go into source, lib, admin, and samples, if you build these utilities, RxStat get process is the one that would actually retrieve those from any server that has these stats enabled. And in fact, that if you're authorized, there are other utilities that can remotely turn this facility on or off on demand, clear the statistics if you want to. So there's a number of nice capabilities in this system. And because it's AFS wide, it really is a useful way to gather information about the types of load that are going on in your cell on any particular server or even on the cache manager. So that's, I just mentioned that in passing. The other thing I'll say about that is that it's called enable process stats, the option that I'm mentioning. And that keeps the statistics on a process level. Obviously, that's where the name comes from. But there's another variation of this called enable pure stats, where it will maintain the same information, but for all of the different clients that are accessing this particular server. And when I say clients, it's not necessarily cache managers. What I mean is client from an RPC point of view. So you could run enable pure stats on the VLserver, and you could see which clients are generating the most load for particular RPCs. Okay, and they're not mutually exclusive. You can do both. You can do enable process stats and enable pure stats, both or none, or one or the other. Okay, so getting back to our use case now, when they used this information to figure out where the load is coming from on the VLserver, this was the RPC that was generating the most amount of load at peak times. And so they knew from just their general instrumentation that at these peak times, the VLserver is the limiting factor, and that is affecting the performance of the entire cell. So this is the first step in figuring out what we need to do to fix this. Let's find out if there's any relation to what type of load is going against the VLserver. And if it's a particular RPC, then maybe we can do something about improving the performance of that RPC. With me so far? Okay. Oh, one more thing about these statistics. Unfortunately, instrumentation in AFS is a little bit confusing sometimes in the terminology and the names of them. There are other performance statistics gathering utilities that have similar names to this but are not related to this. So there are other statistics RPCs that are built into the file server and the cache manager only. And those are retrieved with XStats, FS test, and XStats CM test. So when you start calling these RX stats or RPC stats, and the name of the other command is XStats, but they're not related to each other at all. They're completely different performance instrumentation utilities and facilities within AFS. So just to provide some clarity there. Or maybe I made things more confusing. I have no idea. You'll have to tell me later. Okay, so why are these RPCs taking so long? Because 3.1 milliseconds is an eternity to just look up a volume. Why is it taking so long? And by further investigation, using truss and dtrace, among other tools, they were able to determine that these lookups are taking too long because of excessive VLDB I/O. So each one of these RPCs could generate, on average, 100 read calls into the VLDB. I'm only looking up one volume. Why do I have to do 100 IOs to do that? And it turns out that the excessive I/O for each RPC is because of the way the VLDB is designed. In other words, it's a limitation of scalability issues in the format of the VLDB itself. Okay. Any questions about any of that? Okay. So how is the VLDB formatted? I'm going to go through this in words, and then in a few slides, after we've gone through the content that I want to cover for this particular section of the presentation, I'm going to draw a picture for you, and sometimes that's helpful for people. But the first thing we want to say is that even though it's called the volume location database, it's not really a database. Nothing in UBIC is really a database. What they mean by calling it a database, and the people who wrote OpenAFS weren't stupid. They knew that it wasn't a database too. But what they really intended was a simple way to access a large amount of information using database semantics and using a database-like API where they could say, this is the data that I want, and this is the link that I want, please give it back to me. So what a database really is a giant blob of structures, and it's a byte stream. And so when you want to access something in there at a very lowest level, really you're specifying a raw I/O. You're saying, I want the data from this particular offset into the VLDB, and I want these many bytes. So for a VL entry, you find out from the VLDB structure itself where that particular entry that you want is located, what offset it is into the file, and you know how long an entry is. It's 148 bytes. The code knows that. So it will do a read for 148 bytes there. A logical read for 148 bytes, but I'm getting ahead of myself. So what does the format of the VLDB look like? You have a number of different pieces. First of all, it has to be identified as an UBIC database, so it has an UBIC header. The PT server database, if you are still unfortunate enough to be running KA servers, your KADB has an UBIC data, header on it. But then after that, there's nothing really UBIC specific. That just identifies it as an UBIC header, as an UBIC database. So it has the database version in there and some other metadata about that only UBIC is concerned with. Everything after that, it's a very small header on the front of the database, is application specific. So it's different for every application that is UBIC. And I'll be talking more about that tomorrow, so I'm not going to dwell on that anymore. But for VL servers, the next thing that comes is a VL header, and these are the things that are stored within the VL header. So first we have some very small members. There's a version there. There's a pointer to the last byte in the VLDB. There's a pointer for all of the free slices that are in the VLDB. The maximum vol ID that you've defined so far, that's used when you want to add more volumes. It goes to that and says, okay, how many more do I need to increment that in order to give you the next free volume ID? There's some statistics in there. The next thing that's in there is a table of all the file servers that are in your cell. So it's got information about their IP addresses. It may actually be the IP address, or maybe a pointer to another block that we'll mention here in a minute. The next thing, this is the most important thing for the purposes of our talk, is the embedded hash tables. This turned out to be the place where the bottleneck is occurring. This is the place that causes the excessive IOs. So we'll get back to that in a minute, but let's keep on going. Next thing is the pointer to the first extension block. Extension blocks are currently used for storing additional information about file servers. So I mentioned that there's a table here that may have the IP address of a file server, but it may also point to offsets within one or more extension blocks, up to 4 extension blocks, that give additional information about the file server. Its UUID, if it has a UUID, and other interfaces that file server may have are stored in there. So that's the purpose for the extension blocks. And this is a VLDB4 thing. I didn't really go over the formats, and it's probably not appropriate to do that here. But there were 3 previous versions, and the extension blocks either came in version 3 or version 4, so they're relatively new. This was the original table that only had 1 IP address for each file server. When people wanted to support multi-homing on file servers, this had to be added to the VLDB. Only after we get all that information in there do we start having volume entries. And just as a point of trivia, if you do have more than 1 extension block, the first extension block is always right here. This represents the physical order as well. But if there's another extension block that's added later because we start having more and more file servers in this cell, that extension block could be anywhere because there may be volume entries occupying the space. So it just goes in the next available space. So this is not an accurate representation of where the other extension blocks would be if you had more than one. Okay, any questions about that before we move on? Can everyone hear me okay? Okay. So let's talk about these hash tables. What are they? The purpose of the hash tables is to allow the VLserver to find a volume within the database. Remember I said that at the very low level, all we really want to be able to do is specify an offset and a length and do the read from there. So we need to be able to find out what the offset is for any particular volume we want to look up. If you have a VLDB that's relatively large, you don't want to scan the entire VLDB looking for the volume that you want. And so these hash tables are intended to be an optimization that are built into the VLDB format itself to allow you to find a volume more quickly. And the way that it works is that there are 4 tables in all. Again, these are at the beginning of the VLDB in a fixed size and a fixed place within the VLDB. So there's one for volume names, and there's one each for RO, RW, and backup volume IDs. So 4 tables altogether, they're all the same size. And what they store are simply offsets into the 2 GB maximum VLDB. So a 32-bit integer, that's where the 2 GB comes from. It's assigned 32-bit integer. So we can go a maximum 2 GB offset into the VLDB for any particular entry. And so we only need 32 bits assigned to store that. So this is the hash table is really an array of 32-bit integer places. How do we, and for each of the hash tables, it contains 8,191 buckets. So when I draw the picture of this, it might be a little bit more clear for those of you who need to see things visually. But for now, I just want to say that the only thing that's in the bucket that's in the VLserver, if there's any value in there at all, it's just the head for that particular hash chain, the offset to the first volume, in other words, the first volume entry. And I'll draw a picture for you in a second. But once I'm at that first volume in the chain, how do I find the next volume in the chain? Each VL entry has a member within it on disk that contains the 32-bit offset to the next entry in the chain. And if it's the end of the chain, of course, it says 0. So that's how we're able to navigate through the hash chain to find the volume that we want. We don't have to go through all 2 million because we have these hash tables, but we have to go at least to the end of the hash chain, on average only half of the hash chain, to find the volume that we want. So if these hash chains start to get very long,
unless it's not there.
Unless it's not there, then you got to go all the way to the end.
That was the problem we had, was a lot of people looking for, is my application out there? We check it.
Yes.
When I start up, let me try and load libraries that don't exist.
So that's the pathological abnormal lookup that we mentioned early on. Yeah, it really is the worst case for this particular performance problem. So we had to come up with a separate solution for that. Okay, I talked about the small number of buckets. 8,191 buckets should be enough for anyone, right? But this was designed 20, 30 years ago for relatively small sites. Nobody ever thought that I'd have 10,000 or 20,000, 50,000 volumes in my cell, let alone millions. And so this just doesn't, this hash table, which is embedded and the size can't be changed without changing the VLDB format, is the bottleneck for, it's not scalable for very large numbers of volumes. We're making long hash chains that have to be chased in order to find the volume we want. Okay. These hash chains are maintained automatically, of course, by the VLserver as we add or remove volumes. And the other subtle point that does make a difference in how the performance characteristics of this is that when you do create a new entry, it goes at the head of the chain. All right. Any questions about any of that? Okay, let's move on. Okay, so that's bad that we have fixed hash tables that are embedded in the format of the VLDB. But there's things that make this even worse. I already mentioned that we can't make them any larger without changing the VLDB format. And nobody wants to change their VLDB format because that's Flag Day. And probably some manual conversion as well. So if we start with 1.7 million volumes and we have 8,191 hash buckets, then the average length of a hash chain is going to be about 213 entries. And if you run VLDB check against a VLDB that looks like this, that's exactly what VLDB check will tell you. The maximum length of a hash chain, the minimum length of a hash chain, and the average. And it will be very close to 213 if your VLDB is this size. And that's because the hash functions for both volumes and volume names and volume IDs are well distributed. And that's what you want for a hash function. You want a well distributed hash function so that you don't get some really long hash chains and others that don't have anything in them at all. You want it to be evenly distributed, or I should say normally distributed among all the buckets. So that's bad to have 213 entries in my hash chain. I've got to chase, on average, half of those in order to find the volume that I want. But it's worse than that. You also need to do a read, a physical read, to find the next entry. So I think it's time for our picture. I've come from a mainframe background. I'm a mainframe programmer by trade for many, many years, but now I work on AFS. And so if you work on mainframes for very long, everything is either a square or looks like a disk drive. So I could have made this like a disk drive and you would have no idea what I'm talking about. Instead, I'll make it just a flat square. And I'll draw from the bottom. There's my UBIC header. There's my VL header. I'll just say V there, and I'll say U there. And then in my VL header, I've got my 4 hash tables. And some other stuff too. But this will be going backwards. This is my VK vol ID hash table. This is my RO vol ID hash table. This is RW vol IDs. And this is vol names. And let's just put a couple of entries in here. There's a VL entry. There's a VL entry. So the offset into this, it actually turns out that the offset starts after the UBIC header. So after the UBIC header is our offset 0. And then this is EOF and the file. In our metadata down here, in the VL header, I have an EOF pointer that points up to that, points to the end. So I can find that if I need to. I'm going to switch colors now. Okay, so I have a volume name on the client. I issued a VL get entry by name U command, RPC, to this VLserver. The VLserver will dispatch that RPC to the service thread. It'll look up the volume name, says, okay, I need to find this volume name in VLDB. Hashes the volume name, finds the bucket that it's in the vol names. So let's say that it's in this bucket right here. This is going to be an offset for the volume, the hash chain that contains that volume, but we don't know where it is in that hash chain yet. This is just the first pointer to the first entry. So let's say that that sends us up to this one. So first we have to read this, then we have to read this. And if this is not the right vol name, then we say, oh, that's not the one we're looking for. Another offset right here to the next one in the chain. We got lucky this time. This is the one I wanted, and so there's a 0 in there. Okay. So you can see it's relatively quick if I have a small number of volumes in the hash chain. But if there were 200 volumes here, I would have to do 1 IO for each volume until I got to that place. It might not be a physical I/O because Ubik does a certain amount of caching, but I might be talking about that a little bit more tomorrow. And I'll be touching on it here in a minute as well. Okay, so any questions about that at all? Other than, can I make it bigger? No, I can't make it bigger, sorry. You can come up and look at it later. But you can see that the upshot of that is the number of reads that are required is linear based on the number of volumes that I have to look up that are in a hash chain. You never want to have a linear order for the algorithm that you're using to do anything. So the next complicating part of this whole process is that, as I mentioned, VLserver does do buffering. It has a small buffer pool of 150 Ubik pages. This is configured at build time. There's no option to change this on the VLserver as there is on some of the other servers. I believe this is configurable on FileServer, but that's not an Ubik buffer, it's a directory buffer. But they're very similar pieces of code that handle the buffer management. But my point for mentioning this buffer pool is that it does, because this buffer pool exists, when I ask for that volume at this offset for 148 bytes, which is how long my entry is, that's not what Ubik is actually going to do for me. If it's not already in the buffer pool, then it's going to go get the entire page out of the VLDB that contains that particular entry. So it's either going to be in the buffer pool at that page, or I'm going to go read that whole 1K page and then get it out of the buffer pool. So the fact that this buffer pool is not configurable and is so small, relatively small, is also a problem. If I have to chase a 200 volume hash chain, I'm guaranteed to do on average 100 volumes. And they're probably going to be scattered randomly all through this VLDB. So you can see how quickly I can swamp this buffer. I got that 1K page, I got that 1K page, I got one page, just for one person. I'm not the only person that's doing lookups. If this VLserver has multiple threads for it, then it may be looking up, chasing 100 entry hash chains or 200 entry hash chains for 100 different lookups all at once. So this buffer pool is clearly inadequate to help with that, reducing the I/O at that point. It's actually is useful for one small use case, and that's if you're doing a boss list VLDB, because boss list VLDB does walk this whole thing sequential. That's one of the few commands that does that. So if I get the first one, guess what? Now I've got the next 6 as well. They're already in the buffer, and I only need to do one I/O to get all 6 of the first 6. And so it is relatively quick to do a boss list VLDB because of the properties of the buffer, of the Ubik buffer pages.
It's very interesting to see that the Ubik page structure is 1K.
Yes.
But the individual VLDB records looks like are 148
yes.
bytes.
It's very strange.
So it's not necessarily aligned.
It's because they're using common code. Common code, it's Ubik, so all of the Ubik servers are using that same basic idea of an Ubik page. And I don't know which came first, but there are 3 different implementations of this buffer package in OpenAFS. One for the client, one for the file server, and one for all the Ubik servers. And they're buffering different things, but the code is very similar for all of them. So they have a common heritage, but I don't know which came first. Maybe Todd could tell us that.
So really worst case, you need 2 pages to get one.
Yes, you might need 2 pages to get one if it's spanning a page. Yes, that's correct. Other comments or questions before we move on?
Yeah, I was just saying to Stefan, I could take a picture with my.
You already did.
Okay.
I zoomed it to you.
Yeah, I apologize that diagram is not in the slide, but sometimes it's easier to do it interactively and my PowerPoint foo is weak. So you should be happy that we even got this. I don't use PowerPoint very frequently, so there was a struggle, which we won't get into right now. Okay, so we're ready to move on. This is not the end of it. There are more problems. Physical I/O to the VLDB is done by syscalls. So if it's not in the buffer, then we have to go and read it physically. And we're going to be reading a whole page, and that's done by a syscall. So syscalls are thread synchronous, as everybody knows. But if you're multi-threaded, who cares? That thread will wait while another thread can do something else. Unfortunately, in 1.6 at least, and 1.4, VLserver has been historically running under LWPs, which have already been mentioned several times during this conference. LWPs, we would like very much to get rid of them because they were great in their time for simulating multi-threading on a single processor, but they've far outlived their usefulness in a multi-processor world. They tend to restrict the amount of work that you can get through a particular server. That's LWP, restrict you to one process thread. And when you have an LWP that needs to make a synchronous call to the operating system, then you're doomed because you're blocked on that particular thread and no other thread can run, as would not be the case for POSIX threads, for P threads. So the entire VLserver blocked anytime we have to go do a physical disk read. In this particular use case that I've described to you, the problem is so severe, the VLDB is so big, the load is so high, the UBIC buffer is so small, that we're doing this most of the time. So this also is a limiting factor. And the last thing that I've already mentioned is that new volumes are inserted at the head of the hash chain, but it didn't really discuss the implications of that. What that means is that new volumes that have just been created and probably are either temporary volumes, work volumes, or are not being used very heavily yet because they've just been created, nobody knows about them yet. They're the ones that are the easiest to find. The ones that have been in the VLDB the longest, root-cell, root-AFS, some of your older applications that have very heavy use are going to be out on the end of the chain. That's unfortunate. So the conclusion is that VLserver lookup performance degrades considerably as the number of volumes increases. Once you start getting over 50,000 volumes, you really will start to notice the degradation that all of these problems combined can cause. So how are we going to fix this? Well, we went through a number of ideas. One thing you could do is go out and tune your cache manager to not look up volumes so frequently. You could give it a bigger volume cache in the files. I'm sorry, in the cache manager. That's the dash volume parameter in AFSD. You could make that bigger, and so you wouldn't have to evict one volume in order to look up another one. But if you have to do that for 100,000 clients or 140,000 clients, that gets tired real fast. And what if you need to do more later? So this is not a real answer. What we really want to do is not to monkey with clients, but we want to be able to fix this at the source in the VLserver itself.
Or do both.
Or do both. Yeah, so they're not mutually exclusive. Another thing is I just mentioned the shortcomings of LWP are certainly a contributing factor to this problem. If the VLserver was P-threaded, at least some of this problem would go away because I would be able to issue multiple syscalls in parallel. Not all of them. I'd still be doing lots of syscalls that I don't need to do, but at least one thread wouldn't be waiting on another. I could do more in parallel. The problem at this site is that they were one of the first early adopters for the early versions of P-threaded UBIC, and it had many severe problems, many bugs, many production outages due to this early P-threaded UBIC implementations. And so it's a case of once bit, twice shy, and P-threaded UBIC would be a hard sell for this particular site. So even though it's mostly stable now, 1.8x, and I did test the work that I'm going to be showing you here in a minute. Yeah, we are going to get to it eventually, I promise. But I did test it on both LWP and P-threaded to make sure that the locking was correct when it was transfer it over to p-threaded. So we have to rule out p-threaded UBIC for this particular problem. One solution that was suggested and actually implemented was mapping the VLDB, just map the whole thing in memory. That solves only part of the problem because we still have LWP limitations and we still have the high syscall overhead. So it doesn't eliminate the syscalls at all, it just makes the syscalls faster. So it does help, but it wasn't judged enough to be able to be a permanent solution. Also, it was judged unlikely that doing this would be accepted upstream because who knows why. Sometimes things. Ben, would you accept this if it was submitted upstream to mmap the VLDB?
It doesn't really seem like a good architecture.
Yeah, there you go. So
Kind of same.
yes, it's not sane to do this. And so the next thing we could do is expand those buffers. Those big buffers, we could make them configurable. That's not a whole lot of work. And we could make it big enough that the whole VLDB would fit in the buffer and we hardly ever have to do any physical I/O at all. And that'd be great. But because that buffer code is so old and not well understood, performance characteristics are not well understood, there were a lot of unknowns in taking a gamble on trying to implement with that particular change. So that was never researched or prototyped further, in part because while we were researching this, new information came to light that pointed out the particular problem that I mentioned earlier, which is that the real problem is that it requires too many IOs to look up a particular volume. And loading the entire VLDB into the UBIC buffers just changes that. You aren't going to have the syscalls anymore because I don't have to make the syscall. It's in the buffer. But it just becomes a different scalability problem. We're afraid that we just be moving it from one place to another place. Another thing that was suggested is that if all of the volumes that I really want, the ones I use all the time, are out at the end of the hash chain, why don't we just move them? And that's actually not a difficult thing to do. There's no tooling to do that does that today, but it wouldn't be hard to write a utility or a background daemon task within VLserver that took frequently referenced volumes and moved them up to the head of hash chain. That's not a bad thing. But again, it doesn't really address the root cause. We're limited in how much help that's going to be if you have a very busy cell, because there's going to be constantly new volumes added to the head of the chain. And so you would have had to change where the new volumes go as well. If you put them out on the end of the chain, then you got to be able to find the end of the chain to do an insert. So that doesn't really solve very much. So the proposed solution that we actually implemented is to use an in-memory hash table to cache the contents of the disk hash tables. So 2 hash tables, one in memory. I'm sorry?
It's not 1984 anymore. We have memory now.
Yes, we can use memory. We don't have to be careful about memory. It's so nice. So we were going to come up with a scheme to take the contents of the disk hash tables, and as we navigate those hash tables, we're going to keep or cache the results in memory, and also keep track of when the one on disk changes, so we make sure that the memory one is kept in sync.
Use a larger hash table size than 8,000.
Yeah, that was the first thing we thought. I was like, we don't have to make it 8191 anymore either, even though it's just like those. They don't have to be the same size. But yeah, we could make it twice as big. So that was really exciting that we had twice the performance. No, you'll see at the end that we made it configurable. So the actual hash algorithm that we chose, the hashing table implementation that we chose, is configurable in a number of ways, which I'll get to in a minute. But we also decided early on, or considered, that it would be nice if you have this hash that's in memory, hash table that's in memory, maybe we should just scan the whole VLDB when we come up and put everything in memory. But because there are so many volumes that it takes so long to do that I/O, that was judged to be impractical as well. If your VLserver is out or has to be bounced, we want it to be back pretty fast. You don't want to wait 10 or even 5 minutes for it to come back in order just to get these tables propagated. They're an optimization. It's really not necessary either, because maybe the majority of those volumes will never be looked up. They're just on hand in case somebody looks them up. A job that only runs every month or every year, the volume isn't referenced very often. Why populate the cache with that if we're not going to look it up? So the implementation that was created loads this cache table just on demand. Every time we do a lookup, we cache the results of that, so we don't have to hit the disk again. All right, what are the requirements for this hash algorithm that we're going to choose? There's lots of different hashes tables that we could choose. Which one are we going to choose? We knew right from the start that we need to make these hash chains as short as possible, because that's part of the problem. So making it bigger is going to help, but we also want to make sure that even if we make the table bigger, that it really is implemented well, so that we're not wasting a large table space and still have long hash chains because there's pathological problems with the hash function or with the design of the hash table itself. So we wanted to take great care to avoid making the same mistake that was originally made in the original design of the VLDB. Another thing is that even though memory is cheap, as Andrew was joking a minute ago, we really don't want to waste memory. And most hash table implementations, whether they use a fixed size hash chains, fixed size hash chains or fixed size tables, or I just lost my train of thought. Or either they use hash chains or don't use chains at all. The load factor, the amount of entries that can be put into the hash table based on its size, is generally limited for most of the algorithms that we were able to identify. So for most typical hash functions that you would consider either fixed hash tables or for hash tables that use hash chains, or even those that use the strange, if it's not available here, then I'll put it here instead, and keep on bumping things down, which is a form of doing hash chains in the table itself. All of those start to degrade in performance and in usability once you even start getting close to 50% of a load factor. So we're looking for alternatives that would relieve us from having to waste half of the memory, so that we could have enough elbow room within the hash table to make it operate efficiently with the algorithm that we choose. We also wanted to have reasonable performance. And when I say that, I want it to have a good order. I want it to be a 1, an order of 1 to insert something. I don't want the time it takes to insert a volume to be based on the number of volumes that are already in there. I don't want it to be an ON algorithm like we already have. So we want that to be true for insertions and for deletions, and of course for lookups, which are our most important use case. Some hash algorithms also allow for, once the hash table does reach that critical load factor, I've got a particular hash size and it's starting to fill up, it's starting to degrade, the hash chains are getting longer, we can, at least for some implementations, we can resize the hash table on the fly. We want to avoid that for the VLserver because this is a critical service. We can't interrupt even for a few seconds because of the enormous load that's going through this VLserver. We can't interrupt our processing while we rebuild the hash table in core and then let it go again. So we want to avoid that if possible, resizing or rehashing the existing contents of the hash table. And what we found after doing some research is that there's a strange little hash algorithm called cuckoo hashing. And it has some interesting properties. It's not well known, but some of the distinctives are that it is a fixed size table. It does not use hash chains at all. Instead, it uses buckets. All of the hash buckets have slots in them, a fixed number of slots that in this implementation are configurable. There are a number of academic papers that have been written on this algorithm, and don't want to get ahead of myself. I already said the fixed size and slots, so there's no hash chains. Let me talk about this other distinctive here, the first one, for a second. Where the thing that makes this work is a little bit strange until you read the papers, and that makes sense when you read the papers. But for me to explain it to you, my head would explode. So I'll give the links to the papers at the end, and it will make sense to you when you read it, but you won't be able to explain it to anybody else. It's like taking Fourier series when you're in college, and then when the teacher's explaining, you can say, yeah, that makes sense. But then when you go home and try to do your homework, you can't do it because it seems so clear when it was explained to you, but then you try to do it yourself, and it really is kind of deep. But I do recommend reading the papers. But the magic that makes this work, and I'm going to call it magic because for me, it's indistinguishable from magic. The magic that makes this work is the idea that I'm going to take my hash table and I'm going to split it into two. I'm going to split it right down the middle. So I've changed one hash table into two hash tables. They're both working together to hash the same content, but the two partitions follow different rules. They have independent hash functions, one for the one partition and one for the other partition. And so when I'm ready to insert things into this hash table, this is the process that I follow. In the first partition, I'm going to use that first partition's hash function. I'm going to take my vol name and hash it, find which bucket I need to put it into. And then when I get to that point, I'm going to have a selection of maybe 4 or 6 buckets. Any place, a slot where I could put, in that bucket, there's going to be 4 or 6 slots that I can insert my entry into. And really all I'm inserting at that point is the volume name and the block offset and maybe some metadata for that entry. If there are no empty slots, remember it's a fixed number of slots, either 4 or 6 or sometimes 2, it's configurable. If there's none available, no empty ones in that partition, then I'm going to go to the other partition. I'm going to hash it with the second hash function. Find the bucket for the second partition and do the same thing. Are there any slots available here? If they are, then bonus. It's either, the volume is always going to be either in one partition or it's going to be in the other one. And the magic that makes this support a much higher load factor than for normal hash implementations is this idea that we have 2 hash functions and 2 partitions, and the hash functions are independent from each other. That's the thing that makes this work mathematically. So the interesting thing about this, though, is that what if all of the slots are full? All 4 are full in this partition, all 4 are full in this partition. Now what do? I do a cuckoo eviction. So cuckoo eviction, the name of the algorithm is based on the behavior of a bird called the cuckoo bird. And this bird has a behavior where it does not build its own nests. Instead, it looks for the nest of other birds, kicks out the eggs from that nest and lays its own eggs in that nest and tricks the other birds into taking care of its eggs. So that idea is kind of what we're doing in this algorithm. If I get to the end and I say, I've filled all the slots in this partition for this hash functions bucket, and I filled all the slots in this partition for this volumes bucket, what am I going to do? I'm going to pick one, evict it, and put mine there. So it's always going to be in one of the expected places. It's either going to be in this partition at that hash bucket, or it's going to be in this partition at this hash bucket. I know that. It's not going to be anywhere else. Only 8 places that I can look. All these 4 slots, they're all contiguous to each other in memory, or these 4 slots, they're all contiguous to each other in memory. Very, very fast to search those and to find whether it's free or not. But what happens to the poor guy that gets evicted? We take him, we know his identity now because it was stored in that entry. We know we either know its volume name if this is the vol name hash table, or we know its vol ID if it's the vol ID hash table. We run this same process all over again. So repeat insertion with the former contents of the evictee slot. Repeat as necessary until you find a spare space for that guy. Eventually, you're going to reach a point where you can do this 100 times and still not find a slot because it's getting very full. But you'd be surprised how full you can get this hash table before that starts to happen. This easily supports load factors of well over 80% or even 90%, depending on the dimensions of the partitions, the hash functions chosen, the number of slots in each bucket, and the number of buckets that you choose. So for a well-configured hash table, this is really extremely efficient. It's extremely fast. Insertion, deletion, and lookup are all very well ordered. The space utilization is good, and the CPU utilization is good. So what you could do in the papers and in traditional implementations of this is once you reach this loop limit, you could say, all right, it's time for me to resize this table. But we've already said that one of our requirements is we don't want to resize this table. We don't want to take the time to rehash 100,000 or even 1,000,000 entries in this hash table, make a bigger hash table and hash them all back into that one again. And meanwhile, everybody is waiting for that to happen. We don't want to do that. So instead, what we do is we say, well, he's a loser. He's been evicted from the hash table altogether. And we'll see in a minute that if you choose a good eviction algorithm for which one to evict out of those 8 candidates, if you use least recently used, then you're golden, because this volume is not one that's being used very often, is the one that gets evicted. It's very, very efficient and elegant. Okay, any questions about all that? I know that was a lot. Yeah.
So just a couple things to mention. So I know we were talking about we don't want to rehash like the whole table.
Yeah.
But just I'm not saying like you necessarily want to do this, but there are some hash functions that let you rehash without rehashing all of the entries. There are some that let you do that, and you could just, instead of rehashing stuff, you could just throw everything out. So it's the same.
Yes.
It's the same performance impact as bouncing the server, which is still very fast because it's lazy evaluation.
Yeah. Yeah, that's a good point.
And especially if you like, you know, if we double the hash size every time you do that, you know, you do that less and less frequently as we go on. I think the main downside to doing that is if you don't have a cap on the memory, you know, if you have certain access patterns, you can just, you know, use up all the memory of the machine or something like that. So
Right. Or if
it's probably really important to have a limit, but we could possibly do.
We like 768 gigs of RAM.
Yeah.
How
Also,
much?
we said 168 gigs?
Yeah, so there are ways to maybe like kind of have it not be fixed, to have it expand a little bit. We might want to consider that.
I was going to say, that would have possibilities to add another partition.
Yes. Yes, you could add another partition. So this is the number 2 partition is not a magic thing. The problem with adding another partition is that you have to come up with an independent hash function to go with it. And I can't remember off the top of my head if that's easy to do programmatically with the hash function that we're using, which is Jenkins hash. I know it was very easy for me. I didn't even have to think about it. I just had to pick 2, and I knew that they were independent because of the way that the Jenkins hash is implemented. It makes it easy to find 2 independent hash functions. However, I don't remember whether that was possible to do programmatically.
Well, I think we just, if we did that, you would say, you'd specify a max. So you come up with 10 hard-coded ones, and you just.
Oh yeah, that's a good
so
point.
You start with 2,
Mm-hmm.
and you would add more.
Yeah. Other questions or comments before we move on? Okay. So as I've already mentioned, this has good performance in space utilization and time utilization. Because the resize is optional and we wanted to avoid that if possible, didn't choose any of these other alternatives that were mentioned, they could have served as well. Disadvantage is that there wasn't already an implementation of this in the tree. There were some hashing things that we could have used in the tree, but they were judged not adequate for our use case. So this is not really a well-known thing. I'm sure if you went to school for this, you'd hear about cuckoo hashing, but it's not something that you run into every day. So there was a learning curve associated with implementing this. Here are some papers that you can read if you need some more sleep. And you can see that they're relatively recent. That one at the top is 2004, and that really was the first paper that introduced this idea. So it's a relatively recent academic innovation. I'm sorry?
You said it's recent.
2004 is recent. In the history of computing, going back into the 50s and 60s. Yeah, for an algorithm, yeah.
Good point.
All right. So as I've already mentioned, our implementation is to have 2 partitions, but I'm getting ahead of myself. If you remember from our diagram over here, in the VLDB, we have 1 for volume names, and then there were 3 separate ones, 1 for RW, 1 for RO, and 1 for VK. And I'm sure the person that implemented that in the beginning thought that that was an important thing, distinction to be able to do, because the VLserver RPCs that do lookups by volume ID allow you to specify whether I specifically want an RW, an RO, or a VK, or I don't care. I want you to search all 3. I don't care whether it's an RO, an RW, or VK. Just give me that vol ID, no matter what type it is. So you can constrain the search just by vol ID or by type, and you're allowed to specify a wildcard for the type. I think that's the reason for implementing this as 3 different hash tables, because it makes that particular feature of the RPC itself easier to implement. However, we weren't under any such restriction for when we did it in memory, and so we choose to combine all 3 of these into one, and that made implementation of the memory hash a little bit more simple, easier to understand, I think. So we ended up with, in memory, we have 2 hash tables instead of 4. 1 for the vol names and 1 unified for all of the volume IDs. Each table has 2 partitions. Each partition has a configurable number of buckets, and you're like, we've been joking all along, you're allowed to make it more than 8,191. It's kind of has a geeky interface on it, unfortunately. When I was developing this, I wanted to be able to test performance characteristics. This seemed to be a good way for me to define the size of the table by the base 2 log of the number of entries that I wanted. And that way, I'm ensured that the hash table easily has the properties that I need, which that it has to be a power of 2. The size of it has to be a power of 2 for this particular cuckoo hash algorithm. I'll also mention that each bucket can have a number of slots, and we made that configurable as well. The number of slots by default is 4, but it can be anywhere from 2 to 8. And the papers go into this in quite some depth, evaluating the pros and cons of less slots per bucket versus more slots per bucket. But there is a trade-off there, so that's why I chose the default that I did and the range of possible values that I did. It's based on information that's in those papers. We also needed some instrumentation and debugging, so we added some new VOS commands as well, so we can monitor the performance of the hash tables, get a good indication of when they're started and when they probably should be made larger. Helps with finding bugs in the implementation. If our hit ratio is not what we expect, we can detect that from monitoring the stats. And if there turns out to be a problem with the implementation, we can also dump the entire table and see what the physical contents of the table are using that command.
Question.
Yeah.
So maybe I just zoned out at one point, but when somebody does
understandable.
negative,
Understandable.
Yeah, no, you're doing great. But so I do a search for volume name that doesn't exist.
Yes.
Does that miss get
Yeah.
stored?
So for what we've covered so far, what would happen is it would go to hash it for the first partition, checking all those slots there, it's not there. Hash it for the second partition, it's not there. Then it would go to this and do what we just talked about. It would go to this, which we talked about earlier. If it's not really in the VLDB, it's going to run the whole hash team.
So searching for a name that's not there is always going to be slow.
Correct. What we've discussed so far does not address the negative.
Oh, okay.
problem.
You're not done.
Well,
You're leading up to it.
Yeah.
Got it. Okay, got it. I didn't realize.
No, it's great. It's a great segue.
What?
It's a great segue.
Yeah. Yeah, it doesn't sound negative. Great, go on.
This is why I encourage questions from the audience, is because sometimes it works out.
This presentation's just getting started.
Right. There's
Yeah.
3,012 more slides.
Buckle in.
It's gonna be a bumpy night.
Oh, just a quick note here. You'll see that these command options have funny names, VLMH. This is short for VLserver memory hash, which is the internal shorthand that I use to describe this feature as VLMH or VLMem hash. Okay. As has already been noted, this does not, everything we've discussed so far does not address the worst case of this particular site where people are looking up negative volumes that aren't in the VLDB, both for normal administrative work and also for misconfigured mount points, or for people who are impatient for their mount points to appear or for their applications to appear. And so the mount point is there, but the volume's not there yet. And that's going to generate a pathological lookup. The reason it's pathological is because the hash chains are so long and we have to do so many IOs to get to the end before we know for sure that this volume really isn't in the VLDB. That's not good. So after all of this had been developed, we decided to add on this additional feature, another set of cuckoo hash tables to just keep track, cache the results from negative lookups. So if I don't find the volume after I've run that whole hash chain, I'm going to remember that I already ran the whole hash chain. I don't need to do that again. If 100 people want to look up that volume and it's not there, I'm going to remember that and put that in the negative hash table. And that saves quite a bit of load on the VL servers. Again, we created one table for volume names and one table for volume IDs. The implementation requires that the positive hash tables be turned on. I don't think that was really a design or even an implementation requirement. It just made things a little bit easier, since why implement the negative if you don't have the positive? But I don't think that's a hard and fast requirement. And I haven't really looked at it any further than that. But to configure this, I finally got smart and said that we don't need a huge number of entries in this hash table. So why not just say, you specify the number and I'll work out the power of 2 that makes that work. So this one is much nicer. Probably when this goes upstream, this will be how the other one is configured as well. But for now, the implementation that's in the field right now, and it's been in production for about a year now. Is that right, Ed? About a year?
Yeah.
Yeah. So, and it's on all of their cells. So that's the implementation they have with the funny parameters that I showed you earlier.
And do you keep stats on negative, misses?
Yes. So that they can query those with the VLMH stats command and find out who's the goofball that didn't create this volume yet, or where the bad mount point is. I'm sorry?
Is it relatively infrequent, or is it
Huge. It's quite huge.
Yeah.
quite frequent?
Huge.
Yeah, because you can do an optimization by knowing which part of the disk cache is in memory. So instead of doing the whole search from the beginning each time, you can search from the last chain in a hash. Because you know the linked list.
Yes.
And buckets on disk. If you mirror that in memory, you can follow the chain until you don't have that entry in memory and continue from there. So you don't have to go through the whole 100.
I don't have them stored that way though.
And if you.
Yeah, that's a good idea.
Yeah,
That's an optimization.
Hmm?
That's a good optimization.
Just to interject, we do have the command line parameters, the longer the hash table size for a few things already.
Mhm. Yeah, we already had that a few other places too. But it's not nice. Okay, so how does this work in actual operation? Well, for reads, it's easy. If I have a positive lookup, or if I have a negative lookup, I looked and it wasn't there, I can put that in the appropriate table and keep track of for the next time somebody tries to do that read. They try to look up a volume that's not there, I'm immediately going to find it in the negative table. I'm not going to have to do any IO for that at all. For writes, things are a little bit more complicated, and they're complicated by the fact that at the time we know all the information we need in order to do our hash table operations, the write is not committed yet. So when somebody changes or adds a new entry or deletes an entry, we can't modify to positive cache because it's possible that that work will never be committed. It's a very low chance, but we don't want information in the cache that's incorrect. So instead, when writes are done to the VLDB, when new entries are added or when they're changed, we don't touch the positive cache at all. Instead, the next time somebody would actually try to access that volume, then it's going to be inserted into the cache on the first read. Okay. However, and if some work is done here, let's say that we change the name of an entry and we don't try to mess with that at the time the write is done, but if somebody tries to read that under the new name, when they get to the hash table at that offset, it's not going to be the right one. It's not going to be the right volume. And we detect that and say that's invalid and then continue on with our algorithm. So that may eventually result in a disk read, and then the cache is repopulated with the correct information. So the mistake is found later on when the volume is actually accessed. And we keep statistics on that as well. However, we can't ignore any write activity to the VLDB for negative entries, because if we say that the volume is not in the VLDB and then somebody adds it and our cache says it's not there, that's not good. That's not good at all, because if we can't invalidate it at the time of the write, we're not ever going to know, because the very first read is going to hit the cache that says it's not there. You'll never ever know that it's there unless you do something at the time of the write. So how are we going to work around that if it's not committed? Well, because we're not saying that the volume is present, we're just removing information that the volume is absent. It's safe for us to do that even though the work's not committed yet. It's always safe for us to remove an entry from the negative cache, whether that operation is ever going to be committed or not. So we can do that, but how are we going to do that? It's difficult. I'll get into some details about that in a second. The other case that we have is that quite often, especially in busy cells or big cells, especially if the DB servers are connected by networks that are often congested or have packet drops or are distant from each other, you can run into places where the VL servers have different versions of the database on different VL servers, and then we have what's called a synchronization event. Again, I have a talk on Ubik tomorrow, and I'll talk about that briefly tomorrow. But some of you may be familiar with the idea that there can come a point where a VL server needs to have its entire database replaced from the master, or the master, a new master gets reelected and the current version of the database is on one of the non-masters. And so the database needs to be replaced on the sync site as well. It can go either way. When that happens, we don't want to rehash the whole VLDB. We already said we don't want to do that. Certainly don't want to do it during a resynchronization event because the server is already running. We haven't bounced it. This thing is under active load. And a synchronization event is very disruptive when it happens. You can't process anything else while it's happening, and it can take multiple seconds to transfer a large VLDB. So when this happens, we don't want to do anything with the cache. We just want to throw it all away, and that's what we do. We detect from with Ubik callbacks that a synchronization event is taking place and tell the VL server to throw away the cache for that particular server. One thing I want you to remember when you think about this is that we have typically 3 VL servers, and they all should have the same version of the database. However, each server's caches, memory caches, the disk caches are going to be identical because the VLDBs are identical. But the memory hashes may be completely different depending on what lookups that particular server has done. So there's no way for us to really share caching information between the VL servers. Instead, when there's a synchronization event, we just throw away the cache, but we only have to do it for the server that has been resynchronized, that got the new database. The other 2 still have their memory tables intact. Make sense? You with me with that? Okay. All right, let me go back for a second to this idea that when there is a write, we have to invalidate the negative cache entry on the sync site in all the non-sync sites. Let me just look ahead for a second. I can't remember if I have a slide for this or not. No, I do not. Okay, so just let me discuss this in words and see if you're able to follow me. For the sync site, it's relatively easy because we have the RPC that's the write RPC is happening right there on the sync site. That's the only place where a write can happen is on the sync site. So all the information we need to update the cache on the sync site is present at the time the RPC is being executed. Even though it's not been committed yet, we know the volume name or we know the volume ID. Very easy to just whack it out of the negative cache. And so we do so on the sync site. It's very easy for a sync site. Non-sync sites, not so easy because the way that that update to the VLDB is transmitted to the other sites is not in a logical format at all. It's in a physical format. I want you to, the sync site says, here's the data that should go at this offset and for this length. No semantic information at all. It's just a physical write, a blob of data. So how are we going to solve that? On the non-sync site side, all I'm going to get is an RPC that says disk write or disk write V, and it's a stream of bytes. So what we had to do was create another callback within sdisk within ubic that is for sdisk write, and when it, if this callback is turned on, we examine the contents of the sdisk write data. And if it looks like a VL entry and smells like a VL entry, it's 148 bytes long and has a valid vol ID or has a vol name, then we just automatically remove that from the negative cache. So the same type of safety thing that we do for synchronizations, the same safety thing that we do for writes on the sync site, we are able to do that by cheating on the non-sync sites. It really is cheating to look inside of an sdisk write and try to interpret what that is. And there are many warnings in the comments for that code that say if the VLDB format ever changes, if how we propagate changes to the other sites ever changes, then this isn't going to work anymore. It really is a very gross hack, but it works well. And it prevents us from saying that a volume is not on this VLDB when it really is. Yes?
Does that appreciably increase the amount of time to complete the
No,
validation?
no, not at all. The greatest contribution to adding a new volume to all three VL servers is the latency of the multiple RPCs it takes to do that. So the hash table doesn't add any appreciable overhead to that at all. Yeah.
And again, I probably zoned out early on. The payload of the hash, is that the data or is that just the offset? Or do you always do a read?
The payload of the hash is just the offset.
It's just the offset. Okay.
So yeah, we could talk about that. I didn't mention that in the talk, but yes, we did think about why. I mean, it's not in this talk, so I thank you for raising the point. We did think briefly about just hashing the whole. Storing the whole entry in the cache instead. I honestly don't remember why we didn't do that.
Well, maybe,
We can do-
Do you remember, Andrew?
Well, because the lazy checking, we can check if the value has changed. We don't need to evict things advance. We evict things when we look up and you read it from the database. That's when you do the check to see what's actually.
Yeah. So the canonical copy is on disk. Yeah.
Yeah, we're
Yeah.
just trying to get rid of the on this cache, not the data.
Yeah, I think at the time originally we were a little worried about correctness.
Yes.
So I wanted to rely on the actual correctness of data as much as we could. Of course, you need the negative hash obviously needs to be correct. We have other ways of trying to be conservative about that.
So all this trickery that I just talked about is only necessary when the negative cache is turned on. If you're only using the positive cache, then it's not an issue. But for the negative cache, you have to be very, very careful that you don't say a volume is not present when it really is. That creates all kinds of problems. Okay, we're almost to the end. Thank you for not passing out on me. So in my lab tests, I expected that since I'm doing 1 IO instead of an average of 100 IO, I was expecting 100x improvement. And I never really saw that in the lab. So we were really curious about how this was going to perform in real life. in real life, the RPC throughput increased by about 40x. The reason I can't say more than that is because I don't think you've really reached.
That was the highest we saw.
Yeah, that's the highest that you've seen so far. The highest throughput is 40 times that you've ever seen is now 40 times higher than the highest throughput you ever saw before.
Yeah, so Monday night, for example, 2 a.m., we had a cell that was doing 19,000 per second.
Mhm.
So,
When the previous wall was 325. So
yeah. But it was 320 per server?
yeah, 320 per server per
So
second.
900 something.
Yeah.
So,
hmm
960. Yes.
And that's just for the lookups. I mean, if you have other things going on as well, there are lots
Yeah,
of other
there's writes going on.
Yeah,
there as
but
well.
that one was the critical one.
Yeah, so, and then, every night we have 5 or 6 that are peaking above 10,000 per second.
Yeah.
At a, an interval, not sustained 10,000 per second.
So with this improvement, the VLserver throughput is no longer the limiting factor during peak times. There may be other limiting factors since we aren't reaching the expected 100x. There may be other bottlenecks now that we don't know about, or maybe we just don't need, maybe there's just not enough load there to get it any higher. We don't know the answer to that, but that's where things stand right now. For the future, this has not been upstreamed yet, but the intent is to upstream that. I already mentioned a few things that I would change when I upstreamed this. So that's probably going to be happening later this summer. We get it upstreamed so that the 1 or 2 or 3 sites in the world that could actually use a turbocharged VLserver will be able to use it. Again, this is an extreme case. Many people don't need this, and so it's going to be optional as well. You don't need to turn this on if you don't want to. But for those who need it, it's extremely vital. That's about it. Any questions?
It should be a performance improvement for anyone.
Yeah, I would think so, but maybe it doesn't matter because the VLserver typically just doesn't get that much. It is not a contributing factor to load anywhere. Yeah, you're right.
It won't hurt them to go
It doesn't hurt, yeah.
It doesn't hurt to go faster, right? So let's do
Couldn't hurt.
it.
Any other questions or comments? All right, thank you.